Picture the moment of creation itself, the universe, in an instant of unimaginable energy and light, bursting into being. For a brief, radiant flash, everything was filled with a brilliant, searing glow. But then something shifted. The light faded, the energy cooled, and the cosmos plunged into an era of profound and total darkness. This was not just an absence of stars, it was a silence stretching across billions of years, an epoch so mysterious we're only just beginning to understand its secrets. What happened in that long, hidden chapter of the universe? How did a world of shadow eventually give birth to the first glimmer of starlight? This is the story of the cosmic dark ages, a time before galaxies, before planets, before life as we know it could even be imagined. It's a period so remote and elusive that scientists are still piecing together its clues from the faint echoes left behind. Imagine a universe where no light shone, where hydrogen and helium drifted through an endless, cold expanse waiting. It sounds almost mythical, like a forgotten prologue to everything we see when we look up at the night sky. Yet this era was real, and it held within it the seeds of everything that was to come. The first stars, the first elements, the very architecture of reality as we experience it today. Join me as we travel back to these primordial depths, to a time when the universe was young, dark, and full of possibility. We'll explore how this era of transformation set the stage for the cosmic dawn. The moment light returned, not as a sudden explosion, but as a slow, patient awakening across the emptiness. This journey isn't just about science, it's about our own place in this vast story, and how understanding the darkness helps us appreciate the light. So settle in, open your mind, and let's step into the shadows together. What we discover just might change how you see the night sky forever. To grasp the enormity of this era, we need to understand its starting point. The universe didn't begin in darkness, it began in a state of searing, opaque brilliance. For the first several 100,000 years, the cosmos was too hot and too dense for atoms to form. It was a roaring, chaotic soup of subatomic particles, protons, electrons, and photons of light, all constantly crashing into one another. Light couldn't travel in a straight line for even a tiny distance without smashing into a free electron, effectively trapped in a perpetual, dizzying pinball game. This was the universe as a superheated plasma, glowing with an intense, uniform radiation that filled all of space. But as the universe expanded, it also cooled. And about 380,000 years after the Big Bang, something monumental happened, an event cosmologists call recombination. The temperature finally dropped enough, to around 3,000 degrees Kelvin, that the frantic particles could finally slow down and combine. Protons captured electrons, forming the first stable, neutral atoms, almost entirely hydrogen and helium. This was a cosmic quieting. With electrons now bound securely inside atoms, the pinball game stopped. The photons, the particles of light, were suddenly set free. They could now stream across the universe unimpeded. This moment of liberation is what we detect today as the cosmic microwave background, that faint afterglow of the Big Bang that serves as a baby picture of the entire cosmos. But here's the fascinating paradox. This moment of light's release is also what plunged the universe into its long night. With no more free electrons to scatter it, that initial brilliant light simply stretched and faded as the universe continued to expand, its wavelength lengthening from visible light to microwaves and then into near invisibility. The neutral hydrogen gas that now filled the cosmos didn't emit any light of its own. And with no stars yet born, there were no new sources of illumination. The universe became a vast, dark, and incredibly quiet sea of primordial gas, stretching for hundreds of millions of years. This was the true beginning of the Dark Ages. We often think of darkness as empty or void, but this cosmic darkness was brimming with potential. That neutral hydrogen gas wasn't uniform. thanks to tiny, random fluctuations in density left over from the Big Bang. Some regions were ever so slightly denser than others. Gravity, patient and relentless, began to work on these slight imperfections. Over millions of years, these denser patches started to pull in more and more gas from their surroundings, growing slowly, silently in the absolute dark. They were the cosmic seeds, the nurseries where the first stars and galaxies would eventually be born. So while our eyes would perceive nothing but blackness, this era was a universe quietly, slowly knitting itself together, setting the gravitational foundation for every structure we see in the night sky today. This monumental shift, known as recombination, was less a sudden explosion and more a gradual cosmic sigh of relief. As the universe continued to expand and cool, the frenetic energy of the particle soup finally dropped to a point where stable bonds could form. Protons, once zipping about too fast to make a connection, were able to reach out and capture those free-floating electrons, creating the very first atoms. This process didn't happen in one specific spot. It occurred everywhere at once, a synchronized transformation across the entire cosmos. The primary result was a universe now filled with neutral hydrogen gas, a simple but stable foundation from which everything else could eventually grow. With electrons now bound securely inside atoms, the constant traffic jam of particle collisions came to an end. The photons, which had been trapped bouncing endlessly between particles, were suddenly emancipated. For the very first time, light could travel in a straight line without obstruction. The universe, which had been an opaque, glowing fog, became transparent. This is the moment the cosmos became see-through. If you could have been there, you would have witnessed the blinding initial glow of the plasma suddenly clear, like a dense fog lifting to reveal nothing but an infinite, dark emptiness. That first burst of liberated light is still traveling across the universe today, and we have learned how to listen for its faint whisper. This echo is what we call the cosmic microwave background radiation. It is the oldest light we can observe, a fossilized snapshot of the universe at that precise moment of transparency, frozen in time. The light has been stretched and cooled by the expansion of the universe over billions of years, its wavelengths lengthened from visible light all the way down to microwaves. This is why we can't see it with our eyes, but we can detect it with incredibly sensitive radio telescopes, that faint static on an old analog television. A tiny fraction of that snow is actually from this primordial light, a ghostly signal from the dawn of time itself. Studying this background radiation is like reading a cosmic birth certificate. It's not a uniform signal. It contains tiny, tiny variations in temperature, minuscule ripples that correspond to those slight density fluctuations in the early universe. These ripples are the imprints of the seeds of all future structure. They show us where matter was just a little bit more crowded, the very spots where gravity would later get to work, pulling matter together to form the vast cosmic web of galaxies and clusters we see today. So this afterglow is far more than a relic. It is the blueprint for our entire universe, a map of potential written in light and decoded by modern science. And so, with that final flash of the cosmic microwave background fading into the expanding void, the universe entered its true dark ages. This was not a metaphorical darkness, but a literal, profound, and total blackness. For the first time, there were no light sources of any kind. The initial fireball was gone, and the first stars were still hundreds of millions of years away from igniting. The cosmos became a silent, lightless expanse, a sea of neutral hydrogen and helium atoms drifting through an infinite, cold nothingness. This darkness was accompanied by a dramatic and relentless cooling. The universe was stretching, and as it expanded, the energy within it became more and more diluted. The temperature, which had been a searing 3,000 degrees at the moment of recombination, plummeted. It fell to a point just a few degrees above absolute zero, the theoretical temperature where all molecular motion stops. Imagine the profound cold of deep space today, and then realized the early universe became even colder, a near-perfect void where heat was almost non-existent. This extreme cold was not a barrier to formation, but rather a silent architect. It played a crucial role in the fate of the primordial gas clouds. In a hotter environment, gas particles move with high kinetic energy, making it harder for them to clump together against the pressure of their own movement. But in the deep cold, atoms moved slowly, almost lethargically. This stillness allowed the weakest force in the universe, gravity, to become the dominant player. Without thermal pressure to fight back, gravity could patiently and effectively pull those slight overdensities of gas inward, compressing them ever so gradually. Within this immense dark refrigerator, the stage was being set for a spectacular future. Those tiny ripples in the cosmic microwave background, those faint blueprints of density, were now the central characters in a slow-motion drama. The slightly denser regions acted like gravitational anchors, gently tugging on the surrounding cold gas. Over millions of years, these patches grew denser and denser, forming vast dark structures known as dark matter halos. We can't see dark matter, but its gravitational pull provided the scaffolding upon which the neutral hydrogen gas began to coalesce, forming the very first protogalactic clouds. In the absolute quiet and cold, the universe was silently building the foundations of everything to come. So what was this universe made of during its long, quiet night? The entire cosmic stage was built from just two simple elements, hydrogen and helium. After the fireworks of the Big Bang faded and the plasma settled, these were the only atomic players in existence. For millions of years, they were the entire periodic table. Think about that for a moment. Everything you see around you, the oxygen you breathe, the carbon in your cells, the silicon in the rocks beneath your feet, none of that existed yet. The cosmos was a monochrome canvas painted solely with the two lightest and simplest brushes. Hydrogen was the undisputed king of this primordial era. For every one atom of helium, there were about 12 atoms of hydrogen. This wasn't a chaotic mix, it was a vast, cold, and incredibly diffuse sea. The hydrogen atoms themselves were simple, a single proton orbited by a single electron. Helium, with 2 protons, 2 neutrons, and 2 electrons, was the comparatively complex heavy element of its day. Together, they formed an almost perfectly uniform fog stretching across the entirety of existence. But almost is the most important word in cosmology. While the distribution of this gas was incredibly smooth, it wasn't perfect. The universe was imprinted with those tiny density fluctuations from its birth, the ones we see as temperature variations in the cosmic microwave background. These were the only structures in the darkness, regions where the hydrogen-helium mix was ever so slightly thicker, and regions where it was ever so slightly thinner. The difference was minuscule, perhaps just 1 part in 100,000. To any hypothetical observer, it would have been utterly imperceptible. But in a near-perfect vacuum, even the slightest imbalance is enough for gravity to get a foothold. As the universe continued its relentless expansion, this pristine gas began to cool and thin out even further. The density dropped dramatically. Whereas today we might find billions of atoms in a cubic meter of space, during the Dark Ages, you might find only a few dozen atoms in a volume of space the size of a modern-day classroom. It was the ultimate vacuum, yet within this near-nothingness, the gentle, persistent pull of gravity was already at work. Those slightly denser patches of hydrogen and helium gas began to exert a tiny bit more gravitational attraction than the areas around them. This process was achingly slow. Over millions upon millions of years, these regions acted as gravitational seeds, gently pulling more of the neutral gas toward them. The hydrogen and helium atoms WERE Chinese letter, and slow-moving, offering little resistance. They simply drifted inward, drawn by the faintest of tugs. This was the beginning of structure formation. The hydrogen gas wasn't just a passive backdrop, it was the raw construction material. The helium, slightly heavier, often sank toward the centers of these slowly collapsing clouds. Within the immense dark halos of invisible dark matter, these simple atoms were silently assembling themselves into the first potential homes for future stars. This pristine gas also had a unique property that would prove crucial for the next chapter. It was completely neutral, meaning its atoms were intact, with electrons happily bound to their nuclei. This made the gas largely transparent to certain types of radiation, but it also meant the gas had a limited way to cool itself down. Cooling is essential for star formation because it allows gas to condense into denser clumps. In modern galaxies, dust and heavier elements help clouds cool efficiently. But here, there was no dust, there were no heavier elements. The only way for this primordial hydrogen to shed energy was through a faint, subtle process involving the slight energy shifts of its single electron. This slow cooling rate meant that the first structures to form had to be enormous, setting the stage for the birth of stars unlike any we see today. But in this profound darkness, something invisible was weaving the architecture of the future. The true architects of this cosmic construction were not the hydrogen and helium atoms we've discussed, but something far more mysterious: dark matter. This enigmatic substance, which neither emits nor absorbs light, had been present since the very beginning, and while the atomic gas drifted slowly, dark matter, unaffected by the pressure of radiation, was already starting to clump together under its own gravity, building an invisible skeleton that would define the shape of the universe. Think of the universe at this time not as a blank, empty space, but as a vast, three-dimensional canvas. And on that canvas, dark matter was beginning to trace the first faint lines of a masterpiece. The slight gravitational imbalances from the early universe acted like starting points. Regions with just a tiny bit more dark matter began to pull in more from their surroundings. But this wasn't a simple, spherical collapse. The expansion of the universe stretched these collapsing regions, pulling them into long, thin tendrils and vast, flat sheets. The result was the birth of the cosmic web, a magnificent, interconnected network of dark matter filaments, with dense halos forming at the intersections like dewdrops on a spider's web at dawn. A helpful way to visualize this is to compare it to the most complex structure we know, the human brain. The cosmic web is the universe's neural network. The dense dark matter halos are like the neuron cell bodies, and the long, thin filaments connecting them are like the axons and dendrites, creating a web of communication and structure across a vast, empty space. This framework remained completely invisible, but its gravitational influence was absolute. It dictated the flow of everything. This dark matter scaffolding provided the blueprint and the gravitational muscle. The ordinary matter, the hydrogen and helium gas, was simply along for the ride. As these dark matter structures grew, their gravitational pull became stronger and stronger. The neutral gas, which had been drifting aimlessly, now began to feel this irresistible tug. It started to flow along the invisible pathways, channeled by gravity down the dark matter filaments and pooling deep within the halos at the junctions. These halos became the gravitational wells where the gas could accumulate, cool, and eventually collapse to form the very first proto-galaxies. The formation of this web was a slow, relentless process, taking hundreds of millions of years. It was a hierarchical buildup, with small halos merging to form larger ones, and filaments connecting into an ever more complex and immense lattice. The scale is almost impossible to comprehend. A single filament could stretch for millions of light years, connecting halos that would one day be the homes of immense galaxy clusters. And all of this happened in utter silence and total darkness, a silent dance of the unseen, setting the stage for the moment when light would finally return to the universe. Guided by this invisible cosmic web, the neutral hydrogen gas began a slow, purposeful migration. Imagine a gentle, universe-wide river system with currents defined not by water but by gravity. The dark matter filaments acted as the riverbeds, and the hydrogen gas flowed along these predefined channels, drifting for millions of years toward the areas of strongest gravitational pull, the dense halos at the intersections of the web. This wasn't a rapid or violent process. It was a gradual, almost stately gathering of material. The gas, cold and diffuse, offered little resistance, simply following the gravitational topography that dark matter had carved into the fabric of space itself. As more and more gas streamed into these dark matter halos, it began to accumulate, creating massive, swirling clouds of primordial material. These were the first proto-galaxies, vast reservoirs of potential nestled within the dark matter scaffolding. But for star formation to begin, this gas couldn't just be gathered. It had to be compressed. It needed to collapse from a large, fluffy cloud into an incredibly dense, hot core. This is where physics gets truly fascinating. The collapse was a battle between two fundamental forces, the inward pull of gravity and the outward push of gas pressure. Gravity's job was to pull the gas inward, making the cloud denser and denser. But as atoms are squeezed closer together, they move faster and collide more often, which generates heat. This heat, in turn, creates pressure that fights back against the crush of gravity. In modern gas clouds, this isn't a problem. They are filled with trace amounts of elements like carbon and oxygen, which can form molecules that radiate this heat away into space, allowing the cloud to cool and continue collapsing. But the primordial gas clouds of the Dark Ages were different. They were pristine, pure hydrogen and helium. They had no dust, no heavy elements, no complex molecules to help them cool down efficiently. So how did these early clouds overcome this heating problem? They had one very subtle cooling mechanism, the hydrogen atom itself. Occasionally, a collision between two hydrogen atoms would cause one of them to briefly hold its electron in a slightly higher energy state. When the electron dropped back down to its regular state, the atom would release a tiny amount of energy in the form of a photon, a particle of light. This specific photon had a very long wavelength, which meant it could escape the cloud relatively easily, carrying a little bit of the gas's thermal energy away with it into the void. This process, known as molecular hydrogen cooling, was incredibly faint and inefficient compared to the cooling methods in today's universe. But in the profound cold and silence of the Dark Ages, it was just enough. This slow leakage of energy allowed the gas clouds to gradually lose their internal pressure support. Bit by bit, over millions of years, gravity gained the upper hand. The centers of these vast clouds became denser and denser, and as they did, they fragmented. Large clouds broke into smaller ones, and those smaller clouds broke apart further under their own weight. Deep within these nested structures, in the darkest, densest pockets of hydrogen gas, the conditions were slowly becoming extreme enough to trigger an event that had not occurred since the Big Bang itself, the ignition of nuclear fusion. The universe was preparing to light its first candle, not with a flash, but with the slow, patient gathering of fuel in the deepest corners of the cosmic night. Yet for all its profound influence, dark matter's story is one of absence. It guided the universe's growth without ever directly participating in the chemistry of creation. It sculpted the cosmic landscape, but it could not fill it with light or complexity. That task fell to the ordinary matter it had gathered, the hydrogen and helium gas now pooled within those deep gravitational wells. Within those reservoirs of pristine gas, a new and delicate process was beginning, one that would require not just gravity's pull, but a way to shed the intense heat generated by collapse. The first stars were not yet born, but the conditions for their formation were slowly, silently being met in the coldest, densest regions of the dark. These tiny temperature ripples in the cosmic microwave background are arguably the most important imperfections in the history of the universe. The pattern they form is not random noise. It is a precise map of the initial conditions of the cosmos, a snapshot of the universe at the moment it became transparent. The variations themselves are incredibly slight fluctuations of only about 1 part in 100,000. To put that into perspective, if the average temperature of the background radiation were represented by the smooth surface of an ocean, these fluctuations would be no larger than the gentle ripples created by a single raindrop. They were minuscule, but they were everything. These variations are the direct result of quantum mechanics operating on a cosmic scale. In the frantic first moments after the Big Bang, the universe was so incredibly small and dense that the rules of quantum physics dominated. At that scale, nothing is ever perfectly still. There is always a fundamental jitteriness to reality, an inherent uncertainty. This quantum noise created tiny, random fluctuations in the density of energy and matter. As the universe expanded at a phenomenal rate during a period called inflation, these microscopic quantum fluctuations were stretched to enormous, astronomical sizes. They were literally imprinted across the entire sky, frozen into the fabric of the cosmos as the slight overdensities and underdensities we now detect as temperature differences. So the largest structures we see today, galaxy clusters stretching across hundreds of millions of light years, grew from seeds that were once smaller than a single subatomic particle. The link between a slightly warmer spot in the microwave background and a future galaxy cluster is a direct one. A warmer spot doesn't mean there were more photons there, it actually indicates there was slightly more matter. Here's how it works. In a region of higher density, the gravitational pull was a little bit stronger. For a photon trying to escape that region right at the moment of recombination, it had to climb out of a slightly deeper gravitational well. Climbing that hill cost the photon a small amount of energy, causing its wavelength to stretch just a tiny bit more than a photon escaping from an average density region. Today, we perceive that extra stretch as a slightly colder temperature. Conversely, a region with slightly less matter presented a shallower gravitational well. Photons escaping from there lost less energy, and their light appears to us as a slightly warmer spot. So the temperature map is actually a direct negative imprint of the matter density of the early universe. These subtle differences in density became the universe's architectural blueprint. Gravity is an amplifier of inequality. It always pulls mass from areas of lower density toward areas of higher density. Over the immense span of the Dark Ages, gravity got to work on these blueprints. A region that was just 1% denser than its surroundings exerted a tiny bit more gravitational pull. This attracted more matter from the neighboring areas, making it even denser, which in turn increased its gravitational pull, attracting even more matter. This is a powerful feedback loop known as gravitational instability. What began as an imperceptible ripple slowly, over hundreds of millions of years, grew into a hill, then a mountain, and eventually an entire galaxy cluster. The coldest spots on the CMB map, which signified the deepest gravitational wells and the highest initial densities, became the locations of the most massive structures in the modern universe, like the Great Wall of Galaxies or the vast Coma Cluster. We can see this legacy clearly when we compare the map of the cosmic microwave background with a map of the universe today. The large, faint blobs of temperature variation in the ancient light correspond perfectly with the positions of superclusters and great cosmic voids in the present-day galactic distribution. The patterns match. This is one of the most profound confirmations of our entire cosmological model. It connects the very largest scales of the universe directly back to its very first moments. It tells us that the distribution of galaxies we see isn't random. It's the end result of a growth process that began with quantum fluctuations, was stretched by inflation, and was patiently cultivated by gravity during the long cosmic night. The grand tapestry of the cosmos was woven from threads of unimaginable subtlety. Deep within those slowly collapsing clouds of pristine hydrogen gas, a quiet chemical revolution was taking place. For the first time since the formation of atoms, particles were beginning to bond with one another, creating the very first molecules in the history of the universe. This wasn't a dramatic explosion of chemistry, but a fragile and hesitant process happening in near-total darkness. The primary actor in this drama was the humble hydrogen atom, and its partner was an unlikely one, a hydrogen ion, a lone proton that had lost its electron. The formation of molecular hydrogen, a simple pairing of two hydrogen atoms, was a painstakingly slow dance in the cold vacuum of space. The process began with a chance encounter. Two regular hydrogen atoms, each with its own electron, would rarely ever stick together. They would simply bounce off each other like billiard balls. But if one of those atoms had been ionized, stripped of its electron, leaving just a bare proton, the chemistry changed entirely. This lone proton could act as a powerful gravitational anchor for the electron of a passing neutral hydrogen atom. Through a delicate process known as radiative association, the neutral atom would share its electron with the proton, forming a fragile bond and creating a hydrogen molecule ion, a hydrogen atom linked to a single proton. This unstable intermediary would then eventually find and combine with another free electron, settling into a stable, neutral hydrogen molecule written as H2. This entire sequence was incredibly inefficient. It relied on rare three-body collisions in an environment where atoms were few and far between. The formation of even a tiny amount of molecular hydrogen took millions of years. But that tiny amount was enough to change everything. Molecular hydrogen possessed a special property that single atoms did not, a more complex internal structure. A single atom can only absorb and release energy in very specific, limited ways. A molecule, with its atoms able to vibrate and rotate relative to each other, has a much richer set of energy states. It's the difference between a simple tuning fork that can only produce one pure note and a grand piano that can play a vast range of chords and melodies. This molecular complexity became the universe's first and only air conditioning system. As the gravitational collapse of a gas cloud compressed the atoms, they moved faster and collided more frequently, generating intense heat. This heat created pressure that fought back against gravity's pull, threatening to halt the collapse and prevent the cloud from becoming dense enough to form a star. The molecular hydrogen molecules provided a crucial escape valve for this built-up thermal energy. When a molecule was struck by another atom, it could absorb that collision energy not just as simple motion, but by making its atoms vibrate or spin faster. Later, the molecule could release that excess energy by emitting a low-energy infrared photon. Critically, this infrared light could travel straight through the cloud of neutral hydrogen gas and escape into space, carrying the heat away with it. This slow, steady cooling process was the key that unlocked star formation. By radiating away the thermal energy, the molecules allowed the gas cloud to continue collapsing without overheating. The core of the cloud could grow denser and denser, its temperature and pressure climbing steadily under the relentless crush of gravity. Without this molecular coolant, the first gas clouds might have simply reached a stable, warm equilibrium, forever too puffed up by their own heat pressure to ignite the fires of fusion. The faint infrared glow of these first molecules, radiating out into the infinite cold, was the universe quietly sighing, releasing the heat that had built up since its violent birth and making way for a new, more ordered kind of structure. The stage, once set only by gravity and dark matter, was now prepared for its main actor, the first star. This extended period of darkness, stretching over 400 million years, might seem like a cosmic pause, a vast, empty interval where nothing of significance occurred. But to call it a period of inactivity would be a profound misunderstanding. This long wait was not a void, it was a necessary and active incubation. The universe wasn't simply idling, it was maturing, its components slowly and silently preparing for the monumental transition ahead. Think of it not as a dormant sleep, but as the deep, quiet gestation that must precede a birth. The fundamental reason for this immense timescale lies in the limitations of the universe's only available forces and materials. The initial density fluctuations from the Big Bang were incredibly subtle. The gravitational tugs they exerted were extraordinarily weak. In a universe filled with fast-moving, pressurized gas, these faint pulls would have been instantly erased. But in the expanding, cooling cosmos of the Dark Ages, the environment was finally becoming suitable for gravity's patient work. The atoms were moving slowly, and the radiation pressure that had once buffeted them was fading into nothingness. This created the perfect conditions for gravity to operate, but it could only operate at one speed, slowly. The process of gathering diffuse matter from vast regions of space into dense enough clumps to form stars couldn't be rushed. It was a task of immense cosmic patience, relying on the cumulative effect of infinitesimally small gravitational accelerations over staggering spans of time. Furthermore, the universe itself was working against the process. The relentless expansion of space was continuously stretching the distances between gas clouds, making it harder for them to come together. Imagine trying to gather feathers in a steadily increasing wind. Gravity had to fight this ongoing dilution, working to pull things together even as the very fabric of space was trying to pull them apart. This cosmic tug-of-war further extended the timeline, ensuring that only the most significant overdensities, the ones with the strongest gravitational pull, could eventually win out and collapse. The pristine nature of the gas itself also contributed to the long delay. As we discussed, the only effective coolant was molecular hydrogen, and its formation was a slow, inefficient process. The gas clouds couldn't collapse until they found a way to shed the heat generated by their own compression. This cooling process wasn't a switch that could be flipped. It was a gradual seepage of thermal energy, a tiny trickle of infrared photons escaping over millions of years. The clouds had to cool before they could condense, and that cooling required time, a lot of it. They were essentially waiting for enough molecular hydrogen to form to act as a radiator, and that waiting period was a critical part of the universe's preparation. This extended timeline also allowed for the hierarchical structure of the cosmos to emerge. The first objects to form were not giant stars or galaxies, but small, dark matter halos. Over time, through a gradual process of merger and accretion, these small halos combined to form larger and larger structures. This bottom-up construction was essential for building the massive reservoirs of gas that would eventually fragment to form the first stars. If the first stars had formed immediately in tiny halos, they would have been minuscule and short-lived, potentially altering the entire future chemical evolution of the universe. The long wait allowed for the assembly of the proper cosmic environment, larger, more stable halos that could nurture the formation of significant stellar objects. So, while this 400-million-year era appears to our telescopes as an unchanging blanket of darkness, it was in reality a period of delicate and precise preparation. The universe was utilizing this time to calm itself from its violent birth, to allow its particles to slow down, to let gravity begin its meticulous work of gathering matter, and to foster the fragile chemistry that would enable collapse. It was a necessary period of cooling and quiet, setting the stage not for a sudden explosion of light, but for a deliberate and controlled ignition. The first spark couldn't happen until the cosmic conditions were just right. For hundreds of millions of years, the universe had been a place of quiet, patient gathering. Vast reservoirs of cold hydrogen gas now sat pooled within the deep gravitational wells of dark matter halos, held in a fragile equilibrium. But within the densest cores of these clouds, that equilibrium was finally about to break. The long reign of darkness was reaching its end, not with a single event, but with a slow, irreversible inward fall. This is the moment the first protostars began to form, the first true celestial objects to take shape since the Big Bang itself. This critical transition began when a particular cloud core reached what is known as the Jeans mass. This isn't a fixed number, but a tipping point dictated by a cloud's density and temperature. when the cloud's mass became too great for its own internal gas pressure to support it against the relentless pull of its own gravity, the entire structure became gravitationally unstable. Think of it like a sandcastle on a beach. As long as the sand is dry, it can hold a shape, but if it becomes just a little too wet, its internal bonds can no longer resist the pull of gravity, and it suddenly collapses. For the primordial gas cloud, that extra weight was the final bit of mass that pushed it over the edge, triggering a runaway collapse. Once this threshold was crossed, the collapse itself was surprisingly rapid on a cosmic timescale. What had been a slow, stately gathering over millions of years suddenly accelerated into a freefall that took only tens of thousands of years, a blink of an eye in the history of the universe. The center of the cloud began to contract faster than its outer layers, creating a dense, hot core at the heart of a much larger, more diffuse envelope of still infalling gas. This central object, a swirling, chaotic mass of gas not yet hot enough for fusion, is what astronomers call a protostar. It was not a star in the true sense, but its prenatal form, an embryo gathering mass and heat for its eventual birth. As this core collapsed, the laws of physics dictated its behavior in fascinating ways. The conservation of angular momentum, the same principle that causes an ice skater to spin faster when they pull their arms in, caused the cloud to spin up dramatically as it shrank. This rapid rotation would have quickly ripped the protostar apart, but it was saved by the cloud's own magnetic fields and the chaotic turbulence within it, which helped to transport angular momentum outward, allowing the central core to continue its contraction. Much of the infalling gas didn't fall directly onto the protostar, but was instead flung into a vast, spinning disk encircling it, a protoplanetary disk, though in this pristine universe there were no planets yet to form within it. This disk became the primary channel through which the newborn protostar continued to feed. The energy released during this collapse was immense. As trillions upon trillions of hydrogen atoms raced inward, they constantly collided with one another. The energy from these collisions was converted into heat, and the temperature at the very center of the protostar began to climb exponentially. It passed 1,000 degrees, then 10,000, then 100,000. The gas, once cold and neutral, was now a searing, ionized plasma. For a brief period, this intense thermal pressure was enough to halt the collapse, creating a new, temporary equilibrium. The protostar had reached what is known as the hydrodynamic stage, a massive, puffy object hundreds of times larger than our present-day sun, glowing a deep, ominous red from the sheer heat of its formation. It was a preview of the light to come, a faint crimson ember in the overwhelming blackness of the cosmic night. Deep within the heart of that massive, puffy protostar, a final, critical threshold was approaching. For tens of thousands of years, it had been contracting, its core temperature climbing relentlessly under the immense pressure of its own weight. It passed the 1 million degree mark, then 2 million, then 5. The hydrogen plasma at its center was no longer just hot, it was becoming frantic. The protons, which are the nuclei of hydrogen atoms, were zipping about at incredible speeds, driven by the intense thermal energy. Yet, even at these extreme temperatures, a fundamental barrier still prevented the final act of creation. Protons are all positively charged, and identical charges violently repel each other due to the electromagnetic force. This creates a powerful energy barrier that must be overcome for them to get close enough to fuse. For millions of years, this force had kept atoms apart, but the conditions in the core were now becoming so extreme that a quantum mechanical phenomenon could occur. Occasionally, a proton moving with just the right insane amount of energy could achieve quantum tunneling. It wouldn't slam through the barrier, but rather, thanks to the probabilistic nature of the quantum world, it would simply have a chance to appear on the other side of it, as if a tiny tunnel had briefly opened through the mountain of electromagnetic repulsion. When this tunneling happened and two protons did get close enough, the unimaginably powerful strong nuclear force, which operates only at subatomic distances, could suddenly snap into effect, locking them together. This first step in the proton-proton chain reaction is incredibly rare and slow, but in the massive, dense core of a primordial protostar, it began to happen. One pair fused, then another, then another. With each successful fusion, a tiny amount of mass was converted into a colossal amount of energy, as described by Einstein's famous equation, E equals mc squared. This energy release created photons of light and heat, which began to push outward, adding a new pressure from within the core. For a while, this new energy output simply added to the thermal pressure that was supporting the star against collapse. But then, a perfect balance was achieved. The outward pressure generated by the energy of fusion exactly matched the inward pressure of gravity's crushing weight. At that precise moment, the protracted collapse finally stopped. The object was no longer just contracting, it was now a stable, self-sustaining furnace. The first true star in the universe had officially ignited. This was not a gentle flicker, it was a sudden, brilliant floodgate opening. For the first time in over 400 million years, a powerful new source of light erupted into the cosmos. This was not the fading afterglow of the Big Bang, but a fresh, fierce, and luminous blaze. The star would have switched on like a cosmic lighthouse, its intense ultraviolet radiation blasting outward, violently interacting with the vast shroud of neutral hydrogen gas that still surrounded it. This radiation had enough energy to rip electrons away from their atoms, reionizing the hydrogen in an ever-expanding bubble around the newborn star. This event marked the true end of the cosmic dark ages and the beginning of the cosmic dawn. The universe did not illuminate all at once. It was a dawn in the truest sense, with individual points of light bursting into existence across the vastness of space, each one pushing back its own little pocket of darkness. These first stars, known to astronomers as population 3 stars, were unlike anything that exists today. Born from pure hydrogen and helium, they were behemoths, thought to be hundreds of times more massive than our Sun. Their incredible mass meant their core temperatures and pressures were far more extreme than in modern stars, causing them to burn their nuclear fuel with ferocious speed and intensity. They lived fast and died young, shining with a brilliant blue-white light and flooding the universe with the first complex elements they forged in their furnaces. After an eternity of silence and shadow, the cosmos was finally, gloriously full of light. These first stars were a breed apart from anything we see in the night sky today. Astronomers call them population 3 stars, and they were the universe's pioneering giants. Born from the pristine, uncontaminated clouds of pure hydrogen and helium, they were utterly devoid of the heavier elements that are so common in later generations of stars. This purity, combined with the massive amounts of gas available in their dark matter halos, meant they could grow to staggering sizes. We're not talking about stars merely twice or 10 times the mass of our Sun. These were true behemoths, thought to be anywhere from 100 to over 1,000 times more massive than our own star. Imagine a single star so colossal that it could contain our entire solar system within its diameter, with room to spare. Their sheer size dictated every aspect of their existence, starting with their ferocious brightness. A star's luminosity doesn't just increase with its mass, it skyrockets. A star 100 times more massive than the Sun doesn't shine 100 times brighter, it can shine over 1,000,000 times brighter. These population 3 stars were not just candles in the dark. They were veritable cosmic blowtorches radiating intense, blistering ultraviolet light. This was the key that unlocked the next great transition of the universe, reionization. For hundreds of millions of years, the cosmos had been filled with neutral hydrogen gas, its atoms whole and peaceful. The searing UV photons from these first stars carried more than enough energy to violently rip electrons away from those atoms, reionizing the hydrogen in vast bubbles around each star. This process didn't happen gently. Each massive star essentially carved out a growing sphere of transparent, ionized plasma within the opaque neutral hydrogen fog that still filled most of the universe. It was a fundamental and permanent change to the state of matter, effectively clearing the cosmic air and making the universe transparent to ultraviolet light once more, though on a much larger scale than before. This reionization epoch, driven primarily by these stellar pioneers, set the stage for the universe we observe today, one through which light can travel almost unimpeded for billions of light years. But such a ferocious existence came at a great cost. The incredible mass of a population 3 star created immense gravitational pressure in its core, cranking the temperature and density to levels far beyond those in modern stars. This forced the nuclear fusion engines to run at a frantic, unsustainable pace. They burned through their entire reservoir of hydrogen fuel in a shockingly short time. Some lived for only a few million years. To put that into perspective, our Sun, a relatively average star, has a lifespan of about 10 billion years and is only halfway through it. The first stars lived and died in the cosmic equivalent of a single weekend. Their spectacularly short lives were followed by even more spectacular deaths. A star this massive cannot die quietly. It doesn't gently puff away its outer layers to form a planetary nebula. Instead, its core eventually runs out of nuclear fuel, and without the outward pressure from fusion to hold it up, the entire structure collapses catastrophically under its own immense weight. The result is a hypernova, an explosion orders of magnitude more powerful than a standard supernova, or a direct collapse into a black hole. In either case, these final acts were just as important as their lives. It was in the furnaces of these stars and in the unimaginable violence of their deaths that the universe forged the first elements heavier than helium, the first carbon, oxygen, nitrogen, and iron. They took a universe of simplicity and gave it the gift of complexity, seeding the cosmos with the very materials that would eventually form rocky planets, organic molecules, and life itself. They were brilliant, short-lived titans that fundamentally transformed the cosmos, ending the Dark Ages not with a whimper, but with a series of universe-altering bangs. And so, with the ignition of the first titanic stars, the universe embarked on its next great transformation, an era cosmologists call the epoch of reionization. For hundreds of millions of years, the cosmos had been a neutral realm, its hydrogen atoms existing peacefully with their electrons intact. This state of neutrality is what made the universe so dark. Neutral hydrogen gas is largely transparent to the kind of light we see, but it is incredibly effective at absorbing and scattering the high-energy, short-wavelength light known as ultraviolet radiation. The first starlight couldn't travel far before being swallowed by the fog. The population 3 stars changed everything. Their immense size meant their surfaces burned at searing temperatures, and a hot object radiates most of its energy at shorter, more energetic wavelengths. These stars didn't just glow, they flooded their surroundings with an intense, torrential downpour of ultraviolet photons. Each one of these photons was like a tiny, high-energy bullet. When one of them slammed into a neutral hydrogen atom, it delivered a knockout blow, violently ejecting the electron from its orbit around the proton. In an instant, a peaceful neutral atom was torn apart, transformed back into a charged plasma of free electrons and bare protons, a state the universe hadn't seen since the moment of recombination. This process, known as photoionization, began to clear the cosmic air. Imagine a single, brilliant lighthouse standing on a rocky shore in the midst of an impossibly dense global fog. Its powerful beam would initially only illuminate a small, local bubble in the fog around it. This is exactly what happened around each of the first stars. They each carved out a growing sphere of transparent, ionized plasma within the vast, opaque sea of neutral hydrogen. Inside these bubbles, ultraviolet light could now travel freely. The star was no longer shining into a void. It was illuminating its own little pocket of the universe, the first clear, transparent regions to exist since the cosmic microwave background radiation was released. But these stars didn't just create static bubbles. The ultraviolet radiation exerted a pressure much like the physical force of wind. This radiation pressure actually helped to push the surrounding neutral gas outward, expanding the ionized bubble and preventing the gas from falling back in and smothering the star. It was a self-regulating process. The star cleared its own viewing room, ensuring its light could continue to escape and do its work on the more distant gas. Over time, these individual bubbles grew larger and larger, beginning to overlap and merge with those from neighboring stars. This wasn't a gentle, uniform process like a rising tide. It was a chaotic and patchy transformation, a cosmic Swiss cheese where ionized holes punched through the neutral fabric of space at different times and in different places. The progression of reionization depended entirely on where the first stars and later the first galaxies formed. Dense regions of the cosmic web, where dark matter halos were packed closely together, became the first fully ionized zones. More isolated regions, the cosmic boondocks, held onto their neutral hydrogen for much longer, the last bastions of the dark ages to fall. The completion of this epoch was a fundamental milestone. It fundamentally changed the nature of the universe from one that was opaque to high-energy light to one that was almost entirely transparent, a state it maintains today. This is why we can use telescopes like the Hubble and James Webb to see the light from galaxies billions of light years away. That light travels through largely clear ionized space. The epoch of reionization was the universe's final act of clearing its throat, a necessary cleansing that prepared the cosmic stage for the intricate drama of galaxy formation and evolution that was to follow. It was the moment the curtains were finally, permanently drawn open, allowing the full brilliance of the cosmic dawn to shine through. This flood of light from the first stars wasn't just an illumination, it was a fundamental physical force that began to actively sculpt the cosmos. For hundreds of millions of years, structure formation had been a one-way street governed by the silent, relentless pull of gravity. Gas flowed inward, clouds collapsed, and mass accumulated. But with the ignition of the first stars, a powerful new actor took the stage: radiative feedback. This is the process where the intense radiation from these stellar pioneers began to interact with and dramatically alter the very gas clouds that were the raw material for future stars. The universe was no longer just building, it was now regulating its own growth. The most direct and powerful form of this feedback was photoevaporation. Imagine a dense, cold cloud of neutral hydrogen sitting in the darkness, slowly condensing under its own gravity, perhaps on the verge of collapsing to form its own star. Then a nearby massive population 3 star switches on. A hurricane of ultraviolet photons suddenly bathes the cloud. This radiation doesn't just gently heat the cloud's surface, it violently ionizes it, stripping electrons from atoms and generating intense heat. The outer layers of the cloud are essentially boiled away, the gas heated to such a high temperature that its particles gain enough energy to escape the cloud's gravitational pull entirely. The cloud is effectively eroded, its potential to form stars drastically reduced or completely eliminated. This feedback put a ceiling on star formation, preventing smaller gas clouds from ever achieving the density needed to ignite. But the impact wasn't always destructive. It could also be creative, though in a more complex and delayed fashion. The immense radiation pressure and shock waves from the powerful stellar winds and eventual supernova of these first stars could actually trigger star formation in neighboring gas clouds. A massive shock wave slamming into a stable but dense region of gas could compress it violently, pushing it over the gene's mass threshold and initiating a new round of gravitational collapse. This is a process astronomers see in our own galaxy. in regions like the Orion Nebula, where bright, massive stars are blowing bubbles in the gas and triggering the birth of new stars along the bubble's dense outer shell. In the early universe, this created a fascinating stop-start rhythm to cosmic evolution, where waves of star formation would propagate outward from the locations of the first massive stars. This interplay between creation and destruction had a profound effect on the emerging cosmic hierarchy. The very first stars likely formed in relative isolation within their dark matter halos. But their radiative feedback ensured that the next generation of stars would form under very different conditions. The photoevaporation from the first stars effectively suppressed the formation of subsequent low-mass stars in their immediate vicinity. This meant that to form new stars, gas had to collapse in the larger, more massive dark matter halos that were better shielded from this intense radiation, or that had enough gravitational strength to retain their gas despite the external pressure. The feedback essentially forced star formation to become a more collective enterprise, favoring the growth of larger structures that would become the first true galaxies. This regulatory mechanism also helps explain a great mystery: why we haven't found any of those first pristine population 3 stars. Their feedback was so effective that it likely shut down star formation in their own birth clouds, preventing a second generation from forming there. Meanwhile, the material that was evaporated and enriched with the first heavy elements from their supernova was flung far into space. This enriched material eventually mixed with pristine gas in more distant regions, seeding it with metals. The next generation of stars, called population Roman II stars, formed from this slightly polluted gas. These stars were smaller, longer-lived, and much more similar to the stars we see today. The fierce light of the first stars essentially ensured that their own kind would be a fleeting, singular generation, paving the way for the more stable and diverse stellar populations that would fill the emerging galaxies. The universe's first light didn't just end the darkness, it began a complex dialogue with matter that has shaped the evolution of galaxies ever since. So how can we possibly know about an era that left no visible light behind? We become cosmic archaeologists, sifting through the faintest of echoes to reconstruct a history written in darkness. The primary tool for this detective work isn't a telescope that sees optical light, but a radio antenna designed to listen for a very specific, whisper-quiet signal from the primordial hydrogen gas itself. This signal is known as the 21-centimeter line, and it is our most direct window into the Dark Ages. This fascinating signal originates from a quirky property of the hydrogen atom. A hydrogen atom's proton and electron each act like a tiny magnet, and they can spin in one of 2 ways, aligned with each other or opposite each other. The aligned state has just a tiny bit more energy than the opposite state. Very, very occasionally, a hydrogen atom sitting in the cold darkness of space will spontaneously flip from the high-energy aligned spin to the low-energy opposite spin. When it does this flip, it must release that tiny bit of excess energy, and it does so by emitting a single photon of radio waves with a very precise wavelength, 21 centimeters. In the modern universe, this signal is weak but detectable from nearby hydrogen clouds. The magic for cosmology happens when we look for this same signal from the distant, ancient past. Because the universe is expanding, light from earlier times is stretched to longer wavelengths, a phenomenon called redshift. The 21-centimeter signal from the Dark Ages hasn't just traveled a long way. Its wavelength has been stretched enormously by the expansion of space itself. For a hydrogen atom emitting this signal 400 million years after the Big Bang, that 21-centimeter wave would now reach a stretch to a length of several meters. This means we need to tune our gigantic radio telescopes to search for these incredibly long, low-frequency radio waves, a technical challenge of immense difficulty. The potential payoff, however, is nothing short of revolutionary. By mapping the intensity of this redshifted 21-centimeter signal across the sky, we could effectively create a three-dimensional map of the hydrogen gas during the Dark Ages and the subsequent epoch of reionization. We could see the distribution of that primordial matter and watch in detail as the first stars and galaxies literally turn on the lights, their radiation carving out ever-growing bubbles of ionized plasma in the neutral fog. It would be like watching a time-lapse movie of the universe's first dawn. This is the grand goal of ambitious projects like the Hydrogen Epoch of Reionization Array, or HERA, in South Africa, and the upcoming Square Kilometre Array Observatory, or SCAO, which will span 2 continents. These aren't single dishes but vast fields of radio antennas working in concert to act as a single, colossal ear listening to the universe's faintest signals. They are patiently collecting data, fighting through a cacophony of interference from human technology and even our own galaxy's radio noise, trying to isolate that primordial whisper. The challenge is likened to trying to hear the subtle melody of a single flute being played in a hurricane from thousands of miles away. Yet the scientific community is persevering because the prize is so great. Detecting this signal would not just confirm our models of the early universe, it could reveal entirely new physics. The precise pattern of the 21-centimeter fluctuations could tell us about the properties of dark matter, potentially revealing if it's cold, warm, or something else entirely. It could even shed light on the mysterious period of inflation, the universe's explosive first instant of growth. We are quite literally listening for the birth of structure itself, using the universe's most abundant element as our informant, telling us a story that began long before the first star ever shone. To truly see into this era that left no direct light, scientists have constructed entire universes inside supercomputers. These aren't simple animations, they are incredibly sophisticated digital laboratories running complex equations that simulate the laws of physics across billions of virtual years. The goal is to take our best theories, the blueprint of the cosmic microwave background, the known properties of dark matter and hydrogen gas, and press play, watching to see if the virtual universe that emerges matches the one we actually observe today. It's the ultimate test of our cosmological understanding. Creating these simulations is a monumental task of balance and approximation. The sheer scale is mind-boggling. To model the entire growth of a galaxy, you'd need to track the interactions of trillions upon trillions of particles. This is computationally impossible, so scientists use a clever trick. They represent vast clouds of gas and dark matter with single, simulated particles that each stand in for a huge amount of mass, sometimes thousands or even millions of suns worth. The supercomputer then calculates the gravitational pull between all these particles as they move through an expanding virtual space, all while also modeling complex gas physics like pressure, heating, and that crucial molecular hydrogen cooling. The most advanced simulations, with names like Illustris-TNG and Eagle, don't just show vague blobs of matter collapsing. They reveal the intricate birth of the cosmic web in stunning detail. You can watch the dark matter filaments form first, tracing the same ghostly neural network we theorized. Then, like water flowing into river valleys, the gas drains down these invisible channels, pooling at the intersections. Within those pools, the gas becomes unstable, fracturing into clumps that continue to collapse. The simulations show us that this process is messy and chaotic, full of mergers between smaller halos and violent interactions that funnel gas toward the centers of what will become galaxies. Where these digital universes become truly breathtaking is in their ability to model feedback. It's one thing to simulate a gas cloud collapsing into a star. It's another to accurately show how the light from that first star then blasts outward, heating the surrounding gas, preventing further collapse nearby, and eventually triggering a shock wave when the star explodes that compresses gas farther out, starting the process all over again. These simulations show reionization not as a smooth wave, but as a growing, foamy structure of ionized bubbles, exactly as we predict. They demonstrate how the fierce radiation from massive stars effectively regulates their own formation, explaining why the first generation was so unique and short-lived. The timeline revealed by these digital experiments is remarkably consistent. They show that the long wait was absolutely necessary. The first stars don't flash into existence immediately after the cosmic microwave background is released. The simulations paint a picture of a 400 million year gestation period, where gravity works patiently to amplify those tiny initial fluctuations until the first protogalaxies are massive enough to trigger collapse. Then, within a relatively short window of perhaps 100 million years, the universe erupts with light as these first stars ignite, live their furious lives and die, beginning the process of seeding the cosmos with heavy elements. By comparing the final state of these simulated universes to our actual maps of the large-scale structure of the modern universe and to the observed properties of the most distant galaxies, we can validate the entire model. The fact that the simulations produce galaxies and clusters that look so much like our own is a powerful confirmation that our understanding of the Dark Ages is on the right track. They provide a dynamic, visual story that connects the frozen snapshot of the cosmic microwave background directly to the vibrant cosmic web we see today, filling in the missing chapters with calculated yet compelling detail. This entire grand narrative of the Dark Ages, from the silent pull of gravity to the formation of the first stars, rests upon a foundational assumption that dark matter is cold. But what if that assumption is wrong? The nature of dark matter remains one of cosmology's most profound mysteries, and the properties we assign to it dramatically reshape our story of the universe's long night. The cold dark matter model has been incredibly successful, but exploring alternatives isn't just academic. It forces us to consider how different this primordial era might have been. The standard model assumes cold dark matter, or CDM. This hypothetical particle is heavy and moves slowly relative to the speed of light, which is why it's called cold. This slowness is its defining feature. Because CDM particles aren't zipping around at high speeds, they don't have the energy to escape even the faintest gravitational pull of those tiny initial density fluctuations. They can clump together on extremely small scales very early on, forming those micro-halos that act as the gravitational seeds for everything else. This bottom-up structure formation, where small objects form first and then merge into larger ones, is the backbone of our current story. It allows for the early, efficient growth of the dense cores that eventually collapse into the first stars. But what if dark matter is warm dark matter, or WDM, would consist of much lighter particles that were moving at a significant fraction of the speed of light in the early universe? This high velocity would have a dramatic smoothing effect. Think of it like trying to build a sandcastle with very fine, dry sand. If the sand grains are moving too quickly, they can't stick together to form small, delicate structures. The smallest gravitational wells simply wouldn't be deep enough to hold onto these fast-moving particles. This means that in a WDM universe, the very first structures to form would be much larger. There would be no myriad of tiny dark matter microhalos. Instead, the first filaments and halos would be more massive and appear later in time. This delay would have a direct impact on the timeline of the cosmic dark ages. The first stars might not ignite at the 400 million year mark. They could be pushed back by 100 million years or more. The universe's dawn would have been a later event. Furthermore, the distribution of galaxies would look different. A WDM universe would predict far fewer small, dwarf galaxies orbiting larger ones, as the small-scale seeds for them were never laid down. Astronomers are actively counting these satellite galaxies around our own Milky Way to see if their number matches the prolific predictions of the CDM model or the more sparse prediction of WDM, using the modern universe to test theories about the very ancient one. An even more exotic possibility is that dark matter has some ability to interact with itself or with regular matter through a force other than gravity. This is known as self-interacting dark matter. In this scenario, dark matter particles could collide and scatter off each other, much like molecules in a gas. This would prevent them from forming extremely dense, cusp-like centers in their halos, instead creating more spread out and homogeneous cores. During the Dark Ages, this self-interaction could have smoothed out the distribution of dark matter, potentially making the gravitational wells shallower and thus slowing down the inflow of hydrogen gas. This might have led to a slower, more gradual process of star formation, perhaps even affecting the ultimate size of the first stars, making them less monstrous and more similar to the stars we see today. There are other, more speculative candidates like actions or primordial black holes, each with their own unique implications. The key takeaway is that the Dark Ages serve as a critical testing ground for these ideas. The precise timing of the first starlight, the size of the first galaxies, and the pattern of the 21-centimeter signal we hope to detect are all exquisitely sensitive to the fundamental properties of dark matter. By peering back into this dark chapter, we aren't just learning about the past, we are conducting a profound experiment on the true nature of most of the matter in the universe. The darkness, it turns out, holds the clues to illuminating one of our greatest scientific mysteries. While our supercomputer simulations provide a theoretical roadmap and our radio telescopes listen for the faint whisper of hydrogen, a new generation of observatories is doing something even more profound. They are capturing the light of the first galaxies themselves, turning theoretical predictions into observable reality. The James Webb Space Telescope, or JWST, is our ultimate time machine, engineered specifically to travel back through billions of years and witness the cosmic dawn as it unfolded. This incredible feat is possible because of the finite speed of light and the vast expansion of the universe. When JWST points its massive golden mirror at a distant galaxy, it isn't just seeing across space, it's seeing back in time. The light from that galaxy has been traveling through the cosmos for billions of years to reach us. By the time it arrives, the expansion of the universe has stretched its wavelengths, a process called redshift. The more distant the galaxy, the greater the redshift, moving its light from the visible spectrum into the infrared. JWST is an infrared telescope, specifically designed to detect this stretched, ancient light that other telescopes like Hubble could only glimpse at the very edges of its capability. What JWST is finding is both confirming and completely upending our expectations. The telescope has already observed galaxies that existed well within the first 400 million years of the universe, a time we thought would be dominated by small, fledgling collections of stars. Instead, some of these early galaxies appear to be massive and surprisingly mature, with well-defined structures like disks and bulges. This presents a fascinating challenge to our models. How did these large galaxies assemble their mass so quickly after the Big Bang? Their very existence suggests that the processes of gas accretion and star formation in the early universe were even more efficient and rapid than we had ever imagined. The chemical fingerprints of these early galaxies, revealed by JWST powerful spectrographs, tell another part of the story. By splitting the galaxy's light into its constituent colors, scientists can identify the specific elements present. In many of these very early systems, they are detecting not just the expected hydrogen and helium, but also unmistakable signs of heavier elements like oxygen, neon, and even carbon. This is a direct signature of that first generation of stars we discussed earlier. These elements could not have been forged in the gentle fusion processes of long-lived stars. They are the ashes of violent, short-lived hypernova from massive population 3 stars. JWST is effectively seeing the pollution from the first stellar generation already widespread in the second, confirming that the transition from pristine to enriched universe happened with breathtaking speed. One of the most thrilling discoveries is the observation of these early galaxies actively driving the process of reionization. JWST isn't just seeing passive collections of stars, it's capturing them in the act of blowing gigantic, transparent bubbles in the neutral hydrogen fog. In some images, astronomers can see galaxies that are surrounded by vast regions where the hydrogen has been completely cleared out, ionized by the fierce radiation of their newborn stars. We are witnessing the end of the dark ages in real time, galaxy by galaxy, as they punch holes in the opaque curtain of neutral gas and allow light to travel freely for the first time. The data from JWST is so new and so rich that it is generating as many questions as answers, which is the hallmark of a truly transformative scientific instrument. The presence of these surprisingly large and complex galaxies so early on is forcing cosmologists to re-examine their assumptions about dark matter and the rate of structure formation. Could the properties of dark matter be slightly different than we thought, allowing clumping to happen faster? Or were the first stars even more efficient at producing light and expelling gas than our models predicted? Each new image from JWST is like finding a new piece of a cosmic jigsaw puzzle, one that is revealing a picture of the universe's infancy that is far more dynamic and eventful than we had ever dared to dream. And among the spectacular deaths of these first stellar titans, a new and even more powerful actor was born, the first black holes in the universe. When a population 3 star with a mass of several hundred suns reached the end of its brief, furious life, its fate was almost inevitable. Its core, having fused elements all the way to iron, would suddenly have no source of energy to fight the immense gravitational weight pressing down on it. The entire structure would then collapse catastrophically. For the very largest of these pioneers, this collapse was so complete and so powerful that not even a supernova could stop it. The entire mass of the star's core would implode, falling inward until it crossed a point of no return, the event horizon becoming a black hole. These weren't just any black holes, they were stellar mass black holes of a scale we rarely see today, containing anywhere from tens to over 100 times the mass of our Sun. But their significance went far beyond their size. They were primordial, forming in an environment utterly unlike the enriched universe of today. And they were born hungry, sitting at the hearts of the gas-rich protogalaxies that had given them life. This combination of a powerful gravitational engine and an immense reservoir of fresh fuel set the stage for a transformative process that would further sculpt the early cosmos: black hole accretion. A black hole alone in a vacuum is just darkness, but a black hole surrounded by a swirling disk of infalling gas is one of the most efficient and energetic engines in the universe. As gas from the surrounding cloud was pulled inward by the black hole's gravity, it didn't fall straight in. Instead, it formed a vast, superheated, spinning structure called an accretion disk. Within this disk, particles of gas collided at tremendous speeds, generating intense friction and heat. The temperatures in these disks could reach millions of degrees, causing the material to glow brilliantly across the entire electromagnetic spectrum, from X-rays to radio waves. This process converts a huge portion of the infalling mass directly into energy, often outshining the combined light of every star in the nascent galaxy. This radiation became a dominant form of feedback, far more energetic than that from the stars themselves. The black hole's accretion disk acted like a cosmic blowtorch, blasting its surroundings with intense X-rays and ultraviolet radiation. This high-energy barrage had a dual effect. On one hand, it could be incredibly destructive. It could heat vast regions of neutral hydrogen gas, preventing it from cooling and collapsing to form new stars. It could even photoevaporate entire gas clouds, effectively shutting down star formation in the black hole's immediate vicinity and limiting the ultimate size of its host galaxy. On the other hand, this feedback could also be constructive on a larger scale. The incredible energy output could drive powerful outflows and winds, ejecting material from the center of the protogalaxy at nearly the speed of light. These winds could sweep through the interstellar medium, compressing distant gas clouds and triggering waves of new star formation far from the galactic center. They also played a crucial role in distributing the first heavy elements forged in the depths of massive stars, polluting the pristine hydrogen gas with the seeds of future planets and life. The black hole, through its violent activity, was helping to enrich and regulate the very galaxy it called home. Perhaps most importantly, these early black holes were instrumental in the final stages of reionization. The ultraviolet light from stars was powerful, but it could only do so much. The intense X-rays from accreting black holes had a unique property: they are incredibly penetrating. While UV radiation is easily absorbed by neutral hydrogen, X-rays can travel much deeper into the neutral fog before being absorbed. When they are finally absorbed, they don't just ionize a single atom. They create a cascade of energetic electrons that can go on to ionize many more atoms. This made black holes incredibly efficient at carving out large, persistent ionized bubbles in the intergalactic medium, helping to complete the process of making the universe transparent and definitively ending the cosmic dark ages. The remnants of the first stars, through their transformation into these dark engines, became key players in lighting up the cosmos for good. To truly appreciate the journey from that first moment of transparency to the brilliantly lit cosmos we know today, we need to step back and view this entire epoch on its own grand scale. The story of the cosmic dark ages and the dawn is not one of quick transitions, but of patient, almost unimaginably slow evolution. Let's map out this timeline from the universe's first breath to its triumphant reawakening. Our starting point is recombination, occurring around 380,000 years after the Big Bang. This is time zero for our journey into darkness. In the grand scheme of the universe's current age of over 13.8 billion years, this is incredibly early, like the first minute of a 24-hour day. This is the moment the cosmic microwave background is released, the moment the universe becomes transparent and simultaneously plunges into shadow. From here, the long, silent night begins. The ensuing period, the true Dark Ages, stretches for a staggering span of over 400 million years. To grasp this duration, imagine compressing the entire history of our planet Earth, from its formation to the appearance of the first dinosaurs, into just this single, dark chapter of the universe's life. For all that time, there are no stars, no galaxies, no sources of light. There is only the expanding, cooling sea of hydrogen and helium, and the silent, invisible work of dark matter weaving its cosmic web. This is not an empty period. It is a necessary, active incubation where gravity works with painstaking slowness to amplify those tiny initial imperfections into the gravitational wells that will eventually host the first stars. Then, around the 400 to 500 million year mark, we reach the cosmic dawn. This isn't a single instant where a switch is flipped. It's a gradual brightening, like the first hints of light on the horizon long before the sun actually appears. In pockets across the universe, the very first population 3 stars begin to ignite within their dark matter halos. They are isolated beacons, each one lighting up its own small bubble of space. This era is marked by these individual points of brilliance flaring to life in the overwhelming darkness. Following the dawn comes the epoch of reionization, a process that itself unfolds over several hundred million more years. This is the universe's slow awakening, starting around 500 million years after the Big Bang and completing by around the 1 billion year mark. This is when the collective ultraviolet radiation from countless early stars and the first accreting black holes begins to fundamentally alter the state of the entire cosmos. The individual ionized bubbles around each star and galaxy grow, merge, and overlap, gradually burning away the neutral hydrogen fog that had blanketed the universe since recombination. It's a chaotic and patchy process, not a smooth wave, with some regions becoming transparent long before others. The completion of reionization, around 1 billion years after the Big Bang, marks the definitive end of the Dark Ages. The universe is now permanently transparent to ultraviolet light, and the stage is fully set for the modern era of cosmic evolution. From this point on, galaxy formation and evolution can proceed in a universe we would recognize, leading to the rich tapestry of spiral galaxies, elliptical galaxies, and clusters we observe today. The entire journey from the first atom to the last neutral hydrogen cloud being ionized covers nearly 1 billion years, a testament to the patient, deliberate pace at which the universe constructs its grandest structures. This timeline isn't just a sequence of events, it's a reflection of the fundamental physics that governs our cosmos, where gravity and light engage in a slow dance that ultimately makes a universe capable of hosting galaxies, planets, and life itself. This grand cosmic narrative, from the first stars to the reionization of the universe, is not just a story about the cosmos, it is fundamentally our own origin story. The events of the cosmic dawn set in motion a chain of events that directly led to the existence of planets, oceans, and life itself. Every atom in our bodies, every element on our planet, has a lineage that can be traced back to the crucibles of those first massive stars and the violent deaths that concluded their brief lives. Consider the very air we breathe. The oxygen molecules that sustain us were not present in the primordial universe. They were forged in the immense pressures and temperatures at the heart of a massive star, then blasted out into the void during its supernova explosion. The carbon that forms the backbone of every organic molecule in every living thing on Earth was created through the fusion of helium in stellar cores. Even the iron in our blood, essential for carrying oxygen through our bodies, originates from the final moments of a dying star, produced in the seconds before a supernova or in the merger of neutron stars. The first generation of stars, the population 3 giants, were the universe's first and most prolific factories, taking the pristine hydrogen and helium from the Big Bang and transforming it into the raw materials of complexity. This process of cosmic enrichment did not happen instantly. When those first stars died, their explosive death seeded their immediate surroundings with these newly forged heavy elements. This enriched material then mixed with the remaining pools of pristine hydrogen and helium, gas through turbulent motions and galactic mergers. The next generation of stars, known as population 2 stars, formed from this slightly polluted gas. These stars contained small amounts of carbon, oxygen, and other metals, which made them more efficient at cooling and fragmenting, leading to the formation of smaller, longer-lived stars like our Sun. Each successive generation of stars cooked more complex elements, further enriching the cosmic gas from which new stars and planets would eventually form. It was from this well-mixed, richly endowed interstellar medium that our own solar system coalesced about 4.6 billion years ago. The cloud of gas and dust that collapsed to form our Sun and its planets was a chemical repository containing the accumulated ashes of countless generations of stars that had lived and died over the previous 9 billion years. The Earth itself is assembled from this stellar debris. The rocks beneath our feet, the metals in our technology, and the very atmosphere that protects us are all made of elements that were synthesized in stars that shone long before our Sun was even a glimmer in a nebula. We are quite literally made of stardust, and the journey of those atoms from the hearts of dying stars to the formation of our planet is a direct consequence of the events that ended the Dark Ages. This profound connection has a staggering implication for the potential of life elsewhere in the universe. The same physical processes that unfolded in our galactic neighborhood, the formation of massive stars, their enrichment of the interstellar medium, and the subsequent formation of metal-rich stars surrounded by rocky planets would have occurred in galaxies across the cosmos. The timeline might vary. Some regions of the universe, richer in dark matter halos, may have experienced their cosmic dawn and built rocky planets billions of years before we did. This head start could have provided ample time for life to not only emerge but to evolve into complex and perhaps intelligent forms. The end of the Dark Ages didn't just light up the universe, it set the table for a potential banquet of life, suggesting that worlds with the right conditions for biology could be a common feature in the cosmos, each one a testament to the transformative power of those first brilliant and short-lived stellar titans. While our current telescopes have given us a breathtaking glimpse into this ancient era, the next decade promises to revolutionize our view entirely, moving us from grainy snapshots to a high-definition movie of the universe's birth. The key to unlocking these deepest secrets lies not in capturing starlight, but in perfecting our ability to listen to the universe's faintest radio whispers. Leading this charge is an endeavor of almost unimaginable scale and ambition, the Square Kilometer Array Observatory, or SKAO. Unlike a single-dish radio telescope, the SKAO is a decentralized marvel of modern engineering. It will consist of thousands of individual radio antennae spread across 2 continents, one site in the remote outback of Western Australia and another in the Karoo region of South Africa. When combined through a technique called interferometry, this vast collection of dishes will function as a single virtual telescope with a total collecting area of, as the name implies, over 1 square kilometer. This colossal ear will be exquisitely tuned to the specific, stretched-out frequencies of the 21-centimeter line emitted by hydrogen during the Dark Ages and the epoch of reionization. Its sensitivity will be such that it could detect an airport radar on a planet orbiting a star tens of light years away, allowing it to hear the faint sigh of primordial hydrogen from over 13 billion years in the past. The goal is to move beyond single detections and create a dynamic 3-dimensional map of the early universe by measuring subtle variations in the intensity of the 21-centimeter signal across the sky and at different frequencies which correspond to different distances and thus different times. SKAO will effectively allow us to create a cosmic time-lapse. We will be able to watch in unprecedented detail as the first stars flicker on individually, see their ionized bubbles begin to form and grow, and observe how these bubbles eventually merge to create the vast transparent regions between galaxies. This will provide a direct observational test of our computer simulations, revealing whether reionization was driven primarily by massive stars, early black holes, or a combination of both. But the potential discoveries extend far beyond simply confirming our story of cosmic dawn. The precise pattern of the hydrogen signal holds encoded information about the universe's fundamental properties. For instance, by studying how the signal fluctuates at different scales, cosmologists hope to learn about the nature of dark energy and how its influence has changed over time. It could also provide our clearest picture yet of the properties of dark matter. If dark matter is slightly warm or has other subtle properties, it would have suppressed the formation of the very smallest structures in the early universe. SKAO Ultra High-Resolution Map would reveal this absence of small-scale fluctuations, offering a direct window into the physics of the universe's most mysterious component. Beyond SKAO, other missions are poised to contribute pieces of this grand puzzle. NASA's upcoming Nancy Grace Roman Space Telescope, with its extraordinarily wide field of view, will conduct massive surveys to find the earliest and most distant galaxies, building a statistical census of the stellar populations that drove reionization. Meanwhile, advanced instruments on the extremely large telescopes currently under construction will use powerful spectrographs to analyze the chemical composition of these first galaxies in fine detail, studying the specific elemental fingerprints left by that first generation of stars. Together, this next generation of observatories will transform the Dark Ages from a theoretical chapter in our cosmic history into a richly observed period of transformation. We are on the verge of turning a profound mystery into a detailed chronicle, finally watching the story unfold of how a simple, dark, and empty universe became the complex, structured, and luminous cosmos we call home today. And so we reach the end of our journey back to the very beginning, a voyage that takes us from an era of absolute darkness to the brilliant cosmic dawn. This wasn't just a simple flipping of a switch. It was a patient, billion-year-long transformation where the universe worked in silence to build the foundation for everything that followed. The cosmic Dark Ages were not an empty void but a crucial period of construction, where the subtle blueprints of the Big Bang were amplified by gravity into the vast cosmic web of dark matter that would cradle the first galaxies. Within that invisible scaffolding, the simple elements of hydrogen and helium engaged in a delicate dance, slowly cooling and condensing until they could no longer resist the crush of gravity, igniting the first stars and flooding the cosmos with light. This hidden era shaped every single thing we see when we look up at the night sky today. The distribution of galaxies, the very elements that make up our bodies and our world, and the transparent nature of space itself are all direct results of processes that began in that profound darkness. The fierce lives and explosive deaths of the first stellar giants seeded the universe with the carbon, oxygen, and iron necessary for planets and life. Their light and the radiation from the first black holes painstakingly cleared away the primordial fog, forging the transparent universe that allows us to gaze back in time. We are the beneficiaries of this ancient struggle between light and shadow, our existence made possible by the transformative events of that distant epoch. Reflecting on this, our place in the cosmos feels both astonishingly significant and beautifully humble. We are built from the ashes of stars that died billions of years ago, living on a planet orbiting a star that is itself a descendant of those early pioneers. We are the universe become conscious, able to trace our own lineage back to the first moments of time, and to wonder about the very darkness that made our existence possible. It's a story that connects us not just to each other, but to every galaxy, star, and planet, a shared cosmic heritage written in the fundamental laws of physics. This story is far from over. In many ways, with our newfound ability to peer back into this ancient era, it feels like we are just beginning to read the first chapter. I'm incredibly curious to know what parts of this cosmic journey resonated most with you. Did the sheer scale of the timeline astonish you, or was it the intricate way darkness built the stage for light? Share your thoughts and your own sense of wonder in the comments below. Let's continue this conversation about our grand, shared origin story, a narrative that stretches from the first atom to the conscious mind.